All right, so I assume you all can see a big white screen right now. And let me see what we can do here. So um, if you recall where we stopped, we are working kind of broadly in energy methods. And in the case of anything with solid mechanics, what we're always thinking about is strain energy. And strain energy, you should think of as one possible part of potential energy. It's if you look at a solid structure, there's going to be multiple things that are contributing to the potential energy of that object. That's why we don't just call it potential energy. It's just one part of it, the strain energy, and you can have other things that are going to contribute to the total potential energy of the structure of the material. We first did, so the first thing we did was some scaling. And we said, if we can identify what the two dominant physics are in the system, and we can assume that those physics are trying to balance each other out, then we can literally write down the energy, potential energy of one of the physics. So maybe in this case, maybe in this case something that is like the elastic deformation of an object, and maybe in another case it is the fluid pressure that is going to try and deform that elastic object. And by balancing those, you can come up with a prediction for what's going to happen. And then we learned about Castigliano's theorem. And this allowed us to determine the deflection at a point by considering the partial derivative of the strain energy with respect to the forces applied at that point. Or we could do something where we looked at the angle of rotation, where we took a partial derivative of the total potential energy with respect to the couple at that point. And then we learned some tricks. We learned that you could do, for instance, you could use what's called a fictitious force. Or couple. So you could do that if you wanted to figure out what the displacement or rotation is at a point where there's no force being applied. We also showed that this works for, We also showed that this works for linked systems, discrete, let's say discrete analysis for linked systems, like a truss. And the final thing we did is we showed that this works if we say that we know that the displacement at some point is 0, we can use this to help solve statically indeterminate systems. So we would say the displacement at some point equals 0 equals the partial derivative of the strain energy with respect to the force at that point. So now we're moving on to something new. It's still energy methods, it's still approximate energy methods, but it's going to be based on ideas regarding the fact that everything in the universe strives to everything in the universe is striving to minimize what's called the action. We can think about this in the case of structures by saying that everything is going to try to minimize the total potential energy of the system. Okay. Before we get into that, I'll write that down so you kind of know where we're going. But before we get into that, we have to learn a little bit about something that you probably covered back all the way in statics. But this third step here is a principle of minimum potential energy. And that's kind of where we're kicking off today. And to do that, what we first need to think about is a concept that you likely learned in statics, and that if you're like every other student, it's kind of a weird concept that never feels really, you never feel that comfortable with. And it's this principle of virtual work. And the reason why people aren't very comfortable with this concept is because it relies on a hypothetical or pretend variation. You can think of that being a change of deformation. It's almost like a thought experiment where we almost are trying to basically do the thought experiment as a way to use some tools from math to solve a problem. Okay, you probably recall from particle physics that we would typically write a arbitrary virtual displacement with this like lowercase delta symbol. So we would say a virtual displacement in the u, v, or w direction would be written as, let's see if I can do this. Maybe this will make the handwriting a little better. Would be delta U, delta V, or delta W. So that would be the virtual displacements in three directions, U, V, and W. And so if you have a virtual displacement, then you can think about calculating what the virtual work is. So if we want, we could write the virtual work would be the sum of the forces in those directions times their virtual displacements. Now this is the important part about this. I don't know if this is more distracting. Is this okay with the window up there? Is it distracting to you, or is that all right? Can you see? Yeah? All right, awesome, thank you. The important part is this. If I want to write down the virtual work, it's gonna look similar to the way we would write down work typically. It would look like I'm gonna have the summation of, say, the force in the x direction. Now that's the real force. You never consider a hypothetical or pretend force. What you're trying to consider is you can only vary the displacement. So you're going to have the virtual work would be the sum of the forces in the x direction times the variation in the displacement in the x direction. And so here you see it's the sum of x times du. And so you could do this for all of them. And so I would have sum of the force in the y direction times my virtual displacement in the y direction, and the sum of the forces in the z direction times my virtual displacement in the z direction, oops, which is w. And the principle of virtual work says that if I have a particle in equilibrium, then the virtual work must vanish. Okay, well this is all fine too, because let's see. There we go. The principle of virtual work says that my sum of my forces in those directions must equal 0. Now this is an important point, and I'm going to say this probably multiple times as I'm talking about this concept. What we're saying is that the virtual, the displacement is arbitrary. It's pretend. It can be any value you can possibly pick. So you can just pick a number, and you're saying, I'm going to calculate what the work is if I have this force, and I'm going to vary the displacement at each point in the body by some small amount. And the principle of virtual work says that if I'm in equilibrium, this virtual work must vanish. But the only option there is if delta U, delta V, and delta W can be any possible number times the sum of F of whatever, then the only way that that can vanish is if the sum of the forces in that direction go to 0. And so then you end up with things that are really familiar to you. You end up with the equations of equilibrium, essentially Newton's second law. So this should hopefully be a review, but we can start to extend this to things that are maybe more familiar to us, because we can now think of going from a virtual displacement to an increment or a change in the strain field. Okay, so what does that mean, and how do we do that? Well, what it means is we can write down our epsilon xx in Cartesian coordinates, and we can say, okay, well, what if I would like to consider a variation in that strain? Again, we can only take variations of displacements, variations of points moving in space. So if I want to consider that, I would have to take the variation of epsilon. So I'm going to write my delta in front of it. Okay. And remember, this is going to be the partial derivative of u. Actually, let me do something different here. I'm going to erase this for now and say the actual strain is this, partial derivative of u with respect to x. So if I want to take a virtual displacement and turn that into a kind of a virtual strain, then I was simply, I'm going to vary. The variation in the strain field will be equal to, and this is where the notation starts to get weird. Remember, oops. I have my differential operator, which is still there, times my virtual displacement. I'm going to move that down for clarity. Okay, so you're starting to see kind of new notation appearing here. this is where it's important to kind of remember some of the basic ideas of calculus, in which that partial x is an operator. It's operating on a thing. In this case, it's operating on a displacement. It's just that our displacement is fake. It's this made-up displacement, which we call delta u. Normally, when we have strain, we have partial derivative of u with respect to x. And now all we're saying is, well, let's just look at a variation where in our strain field. So I'm going to kind of perturb that strain field by a small amount. And I'll be able to calculate my variation in my strain field by taking the partial derivative of a variation of u with respect to some displacement here. And so here's this notation that you're going to see over and over and over again. And that is that you're going to have the variation, let's see here, the variation in something, oops, is going to be equal to the partial derivative times the variation in the relevant displacement. So the way you're going to actually see this most often in this course, or in any time you're dealing with these energy concepts, is thinking about this in terms of the variation in the strain energy. Because really what we want to be able to do is talk about minimizing the total potential energy. In order to do that, we have to think about the variations in the strain energy. And what we want to be able to do is say, what is the variation in strain energy? And this is typically written like this. So we would say I'll have delta big U is equal to the partial derivative of U. Now this is strain energy, not the vector, with respect to, say, some displacement. Maybe we could say, for sake of clarity, we'll call it just some displacement. We'll call this displacement A, and times this virtual displacement. Okay, so let me dissect this for a second. This is our virtual displacement. And now we have to deal with what this delta U means. So what is this thing over here? So what's this? Well, we can figure that out because I just showed you up here what the variation in the strain is. And so if I want to calculate the variation in the total potential energy, then I will scroll down here. I will say, okay, well, what's delta U? Well, delta U is equal to the integral over the volume of the body. And you know, strain energy is stress times strain. So the variation in your strain energy is going to be stress times the variation in strain. Okay, so that's fine. So we have sigma xx times variation in epsilon xx, which we know how to calculate. Sigma yy, variation in epsilon yy. ZZ, variation in epsilon ZZ. All of these are going to look exactly like what I wrote above it right here. Okay, but now we have to think about the shear stresses and shear strains, and so that's going to be a little bit complicated. So I'm going to write them down, and then I'll show you what they are. So for instance, let's consider XY. So we'll have the stress in XY times the variation in my shear strain, which would be variation in gamma XY, and then so on. So I'll have stress in XZ variation in gamma xz, yz, variation in gamma yz, and that's all integrated over the volume. Okay. Now, that's not too helpful yet because you know what everything is except, let's say, this term. And it's sort of similar to the normal strain, but it's a little bit more complicated. So we have to remember that shear strain has an x and a y, which means there is strain in two directions. So the variation in gamma xy is going to be equal to the differential operator in the x direction times the variation in the y direction plus the differential operator in the y direction times the virtual displacement in the u direction. So it's a little bit more complicated because you have to consider the fact that those shear strains have two directions to them. So there's going to be partial derivatives in two directions for those. All right. Hopefully, how are we doing so far? Let's take a minute and I don't know if this is review or new. I would imagine everything up to, say, this is review, but maybe this stuff is not. I don't know. I think maybe that's fair to say. Any questions? Let me see if I have the chat window. There we go. There it is. Okay. Questions, comments, thoughts, either verbally if you're comfortable with it, or you can just throw something in the chat window. Nothing? All right. Okay. The principle, if you remember what we did in the scaling arguments, we said, what are the two energies that matter? Let's set them equal to each other and see what happens when we balance them. So what I didn't tell you is what we were doing with that was actually using this principle of minimum potential energy. And the principle of minimum potential energy is kind of like a subset of this bigger principle, which is the principle of least action. Okay, so what does that mean? It says when we dealt with the scaling arguments, we would calculate the energy in one case and balance it with the energy in another and look for them to be equal. This is all we're doing right now is saying if we can simply compare the variation in the strain energy to the variation in the work being done or the virtual work being done, then we can equate them and use that to approximate deformations. Okay. So we have half of it, but we need the other half. The other half is going to be what the virtual work is. And so virtual work I described before, but not quite in the way we're going to use it. Good question. Okay. So there's a question in the variation of the strain energy, what is delta U? And so I think that's referring to this thing here. Oops, I lost it. There you go. These are the virtual displacements. This is the part that always trips people up. So let me draw something over here. So I'm going to remove, let's get that thing out of there. What we're really doing is we're saying, okay, I've got this 3D body. This is my block of rubber or something. And I could look at some point up here in real space, that's where that point is. I can put a coordinate system on here and say, that point exists in space somewhere. And what we're doing is we're saying, let us take that point and virtually displace it. So that means literally I'm going to take it, in the case of delta U, I'm going to take that point and move it a tiny amount. I'm exaggerating this drawing, so that arrow there should be infinitesimally small. But I'm going to move it over to here, such that now my body is going to have a virtual displacement. Oops, that's probably. That is this amount delta U. The delta is to represent the fact that we didn't really displace it. There's nothing actually moving that point. What we want to do is imagine we have some small displacement in X or Y or Z, calculate the strain energy, and then say, well, we have to find the one that's smallest. And the one that's smallest should say, well, if we're in equilibrium, it should, no matter what size of that variation, we should get the correct strain energy out. So it's almost like calculating what the change in energy is in a system if you were to take a point and move it a little bit. But we don't really move it, we just pretend move it. And we just pretend move it. And the reason why the movement is fictitious or pretend is what we're going to find, the principle of virtual work and the principle of minimum potential energy, what that's going to tell us is no matter what size delta U is, and no matter if we have additional virtual displacements of this point in delta V or in delta W, no matter what magnitude, no matter if we have all three of them or just one of them, the structure is going to find the shape where the total potential energy is at a minimum. And so the magnitude of those displacements doesn't matter. And that's why it's this pretend like mathematical trick. If this isn't very clear to you, that's okay. What I'm going to do is I'm going to just give you the equation for the virtual work. I'll write down what the principle of minimum potential energy is, and then I'll try to show this to you to me, this is my favorite thing to teach because I find it to be really beautiful and really kind of eye-opening, and I think it'll help understand what these virtual displacements are. So if we're mostly clear, great. If not, give me like 10 minutes and then I'll kind of go through what I think might help this a little bit more. So virtual work is going to have the same approach here. Virtual work is even easier. Virtual work is going to be over here. We're going to say, well, my virtual work, we're going to call work W. So the virtual is going to have the delta in front of it. That's a big capital W. And I'm going to say, again, I'm going to integrate over the volume because I have an elastic body, not just the point mass. I'm going to integrate over the volume. I'm going to have my force in the X direction times my displacement in the U direction, and then so on and so forth. Force in Y, displacement in Y, force in Z, displacement in Z, integrated over the volume. Whoa, what the heck happened there? There we go. These are body forces per unit volume. Body forces per unit volume might be gravity, magnetic force, something that's acting on the entire body. We often deal with traction forces or surface forces, forces that are acting kind of per unit area on your elastic body. So we have to add an additional term to this virtual work, which is going to look like an integral over the area of, let's call this Px delta U plus Py delta V plus PZ delta W over the area. And now this Px is a surface force per unit area. And this F of X is a body force per unit volume. Okay. This isn't that crazy. This looks basically just like what I wrote before, but just instead of summations, we have integrals, and so it shouldn't be too different. The total work done during this virtual displacement must vanish for the same principle as before. This principle of virtual work tells us that we should have the difference between the work and the strain energy to be 0. Or said a different way, I should probably draw a line there. Hold on 1 second. Let's do that. Okay. This is the principle of virtual work. Something that connects this is this idea that essentially we need to minimize the total potential energy. So the total potential energy is going to be the strain energy minus the work being done. So let me write that down. So the principle usually the total potential energy is written with a capital pi. That's a super annoying variable choice, but it's not mine. Total potential energy is the strain energy minus the work. And because of our principle of virtual work, we could say that the variation in our total potential energy is equal to the variation in my strain energy minus the variation in my work. When this thing is equal to 0, it's referred to as stationary. The potential energy is at a minimum. Okay.
Hey, Professor.
Yes.
So, in this case, the potential energy will never be less than 0, right?
Correct. Yeah. Well, let me say it a different way. For the Yes, it'll never be less than zero. The second variation of the total potential, you can just keep doing this. You can keep doing like second derivatives and squared displacement. So like virtual displacement times our virtual displacement times the second derivative of your strain energy, and that's how you check for stability. Now that can be above, greater than zero, or less than zero. The simplest way to think about that is, and this is like not just an analogy. It actually is almost like a direct way of kind of imagining this. You can imagine you have, I'm gonna draw this so it's easier. You've probably seen this before, and so if you have, this will just be a brief reminder. Remember, equilibrium is just saying that all the forces balance. And so this is like, you might say, okay, well, I have a ball. Well, that's a terrible, terrible drawing. Let's try that again. I have a ball on the ground, and its gravity is going down. There's a reaction force coming up. This ball is in equilibrium. Now, you can do that again, and you can say, well, I could put that ball in the bottom of a bowl. And that ball looks like it's in equilibrium. What we're doing when we say that is actually we're doing in our head this virtual displacement. And that'll be more clear when you think of it this way. If I take my ball and I put it on a hill like that, I would say, oh, okay, something looks off. And what we're actually doing here is we're actually doing this virtual displacement. What we're thinking is, what happens if I take this ball and I give it a slight displacement in that direction? And the question we are asking ourselves is, does it come back or does it keep going? If it comes back, then it's in a stable equilibrium state. If it keeps going, then it's in an unstable equilibrium state. So if I take this thing, we all know that this is in equilibrium. There's forces that are balancing, gravity and reaction forces here. But if I take this and I virtually displace it a small amount, delta U, it's going to roll off that hill and never come back.
Okay, yeah.
And so that's where this idea of, and this refers to, so this tells us, I should probably be clear, this tells us that, let's see here. This tells us we're in equilibrium. Each of these things are in equilibrium.
Okay.
What we need to determine if we want to check for stability of equilibrium, and that's what we're really looking at with these pictures, is stability, is we need to check, this is just like calculus, right? You say, okay, hey, I've got a curve, I need to figure out where the maximum or minimum are, I take the function, I take the derivative of that function, I set it equal to 0, and now I find my stationary points. But just like in calculus, you never know if you have a maximum or a minimum. And so you need to, if you want to figure out if you have a maximum or minimum, you have to take the second derivative of that curve and determine if it's positive or negative, determine if the curve is convex or concave. That's the same thing we're doing here. And so if we would want to figure out if this thing is stable, we would look at the second variation. So it would look like this. This is just conceptual right now. You don't have to worry about how to calculate this. I'm just giving you the idea. We would have to ensure that this is greater than 0. This one will be equal to 0. That's terrible. Let's try that again. And this one will be less than 0. So equilibrium is determined by the first variation of your total potential energy. Stability is determined by your second variation. So in equilibrium, you're not going to have a negative value here, but in stability, you may. And if you do, you're unstable. And that's what that would look like.
Okay. Thank you.
Let me write down that just to be clear. Unstable, but still in equilibrium. So it's unstable equilibrium. Stable equilibrium. And this is what's referred to as neutral equilibrium. It doesn't really matter. Nothing. It's not, the energy is not, the potential energy is not changed as you displace this thing in the x direction. All right. So here's the best way I know to explain this. And we'll just give it a go here. I am based what I'm about to give you is my bastardization of a famous Feynman lecture. So if you want to see this done properly, I think Caltech has all of Richard Feynman's lectures online, and I think this one's not in the books, or maybe it's at the end of it, but you should look it up. If you just Google Feynman and then principle of least action, then you can go through this independent of here. But I'll try to do my best Feynman impersonation from here. So principle of least action, principle of minimum potential energy, they're the same. Principle of least action is broader because it encompasses dynamical deformations, whereas principle of minimum potential energy, there's no kinetic energy. But for the sake of illustrating some of these unclear concepts, like what's a virtual displacement, why do we use a virtual displacement to learn something, this can be useful. For right now, don't worry about the math. We'll come back to it later in the semester where we have to learn some of these tricks for elastic structures, but you can kind of just try to make sense of this conceptually and not worry about any of the math going on. And so the idea goes as follows. Let's take a ball and throw it from here to there. Okay, so what does that mean? So I'm going to take a ball from here and I'm going to throw it to there. And we're going to know, we know that our ball is going to follow some trajectory as it goes. It's probably going to look like that. That's the actual motion of the ball. So this vector is the actual motion. Now, we could imagine that the ball is going to take a different motion from here to there, a different trajectory from here to there, but getting there in the same amount of time. So imagine that we throw a ball and it gets from here to there in the same amount of time, but instead it goes this way. Or it could go this way, or this way. Any possible trajectory is admissible here. We can imagine any one we want, and we could say, imagine our ball is going to go from here to here in some imagined motion. Okay. So here's the key with the principle of least action. If you calculate the kinetic energy at every moment along the imaginary path, and you take away the potential energy at every moment along the imaginary path, and you integrate this over the entire time, over the entire path, you will always get a larger number than the true actual motion of the ball. Let me say that again. The average kinetic energy minus the average potential energy is always as little as possible so we can math up this statement here. We can say, okay, well, let's actually like do something real. Let's put some coordinates on here. We'll call that the x direction. We'll call this time. We'll say my ball is going to start at some position T1 and is going to end up at some other location at T2. And it's going to take this path, which we can denote by x bar of, ooh, that's terrible, hold on. X bar of t. And if we have this motion, then we can write down the kinetic energy. This is often referred to as capital T. Okay. Which we know from, since this is just a particle, it's just very simple to write down. We can write down this is going to be 1/2 m times v squared, but v is going to be the derivative of our displacement vector. So it'll be dx bar dt squared. And for the sake of the potential energy, we could think about this in a gravitational field, but we'll just write it down more generally and say that it's going to be called v, and we'll just write that as v of x bar, some unknown function v of x bar. It won't, it'll make it easier for us to do this calculation out. So I'm going to zoom in over here so I don't write terribly. Okay, that's pretty bad, but okay. So I said before, if you're, as I was kind of chatting, I was saying if you take the kinetic energy at every point, take away the potential energy at every point, and integrate along the time that this curve is traveling from T1 to T2, you're going to get a number, right? You have an energy and an energy. You integrate that over time, you're going to get a scalar, some number. That number has a fancy name, as you can guess from the principle. It's called the action. So what's the action? The action is what I just said, but in math. So the action is denoted by capital S. And like I said, this is mainly for your intuition, not for, don't worry about any of the details here. We'll come back to a lot of this. But again, we're going to integrate from T1 to T2, and we're going to integrate the kinetic energy minus the potential energy. So it's T minus V over dt. But we can say, well, I know what that is. It's really the integral from T1, T2 of 1/2 m dx bar dt squared minus v of x bar dt. So really, if you look at what this is saying, is the average kinetic energy minus the average potential energy is always as little as possible. So what you want to do is impossible. What you want to do is you want to calculate the action for every single possible trajectory and then just find the number that's smallest, and that's the path. But clearly you have to do that for an infinite number of paths. That seems like a pretty impractical way of doing it. But this concept of a virtual displacement or a virtual motion is going to help us here. So this sounds like a calculus problem, right? This sounds like, I kind of alluded to this a few minutes ago. I said, well, hey, all we need to do is maximize or minimize a function. We know how to do that. We take derivatives of the function. Great, this is no problem. Except that we're not dealing with functions here. Usually, if I take the derivative of a function, of some variable, I'm going to get some value that tells me where the maximum is, right? I've got some curve. I'm going to take the derivative of that curve with respect to some coordinate, set it equal to 0. I'm going to find the point at which it's a maximum. But if you look at what we're doing, I'm not looking for a point. I'm looking for a curve. So I'm looking for a path that's going to minimize the action, not a point. And the reason why this is a problem is because we don't have functions. We have a function of a function of a variable. And that's more complicated. We have, so the action S is a function of t and v, which are functions of x bar. Or more mathy, we would say S is a function of, t, which is a function of x bar, and v, which is a function of x bar. So these are not, S is not a function, so we can't just take a derivative of it. S is a functional. We need new calculus. We need a whole, this actually led to the development of an entirely new branch of calculus called the calculus of variations. Okay. Questions so far? Should just be kind of particle maths up until this point. But now we're going to actually introduce a new way of calculating minimums, which will hopefully, is my hope, kind of explain this idea of these virtual displacements or virtual motions. So what we're going to do is we'll go back to our curve here, and we will say that I'm going to imagine some pretend virtual curve. So here's my pretend curve. It's going to be in orange. The first thing I want you to know is that my pretend curve, my virtual path, my imaginary path, starts and ends at the same points as my original paths. That's going to be important. And so keep that in mind. My virtual path is going to start and end in the same locations. That's kind of crucial. We can call this path x of t. And at every single point, there's going to be some difference between my actual path and my imaginary path, which we're going to call eta of t. Okay, so now we can go back over here, and instead of x bar, we can replace x bar with x plus my virtual difference between the imaginary path and the real path. Okay, so I'm going to write that down here. I'm going to say, okay, my new S is equal to integral from t1 to t2, m over 2. Now I have dx bar plus dt, I'm sorry, over dt plus d eta dt squared minus v of x plus eta.
Is it possible to zoom again as before?
Yes.
Thank you.
Like, better?
Yeah, thank you.
Excellent, okay.
Excuse me, Professor. Shouldn't dx be without bar?
I was just thinking that too, actually. I'm glad that you asked that because I was just looking at my notes and for some reason it's not without the bar and I don't know why. So why is it not without the bar?
Because x bar is x plus eta, maybe.
I think that's exactly what it is. So now I think what I'm doing is I'm writing down, so let me try to do this here for you. I think what I'm doing is saying, I want to calculate the action S. Yeah, you know what, this is gonna make things easier. How about this? Give me 1 second. I'm gonna say up here, this is really the action of the true path, like the actual X bar action. So now I come back down here and I can say that what I'm looking for is S of t of x and v of x. And I have replaced x with, where did that go? Oh yeah. X, what did I do? That seems like I did it wrong too, doesn't it? Oh, haha. I screwed up this part. Okay, so sorry everyone. This I messed up. X is equal to x bar plus eta t. So now that should make more sense. Does that make more sense? I just screwed up my notation up here. So this is x bar t plus eta t. And so now this should be okay. Does that clear things up?
Yes, yes, it does make sense.
Okay, perfect. Sorry about that. Okay. So now what do we do? Well, now what we do is we can say, this is a quadratic. Let's just expand my quadratic. So I'll do that in a different color. We'll do that in blue. So this thing here is going to be, actually, hold on, let me just expand. I'll just expand this part. Is going to be dx bar dt squared plus 2 times dx bar dt d eta dt plus d eta dt squared. And what I want you to notice is that this term is first order in eta, and this term is second order in eta. And that'll be important in a second. Okay. I haven't done anything crazy. I just said we're going to take an imaginary path, which we can write as the original path, the true path. Even if we don't know the true path, we can just say, I can take any imaginary path and say the imaginary path is going to be the true path plus some small perturbation, eta. Okay, and that's what I've and then I just substitute that into my action here. So we've dealt with the first term in the action. Now we have to deal with the second term in the action. So the next thing I'm going to do is deal with this here. And so we'll do that down over here on a new page. So what do we do with V x bar plus eta? Well, we don't know what this is. So all we know is we've got some arbitrary function that's got stuff in there, x bar and eta. And so what we do is we say, we know that our perturbation, our virtual displacement, our virtual path there, the difference between the true path and the fake path is small. We're going to just assume that we're just going to look for paths that are really close to the original one. So we're going to assume eta is small. And if eta is small, then we can write this as a Taylor series expansion. We can say that I can do a series expansion where I say V x bar, I'm expanding around eta is equal to 0. So I'll write this down in a second, but I'll first tell you what the answer is. So this is a Taylor series expansion about eta equals 0. And now again, you see the same thing. We do this series expansion here. This is first order in eta, and this is second order in eta. Okay. So now we can go back to our action, which we were writing in pink. So let's do that again. And we can just substitute everything back in. So we can go back to our action, S. And since eta is small, the only thing I'm going to do is I'm only going to keep the first order terms. And I'm going to write that with a mathematical notion like this. And I'm going to collect all those higher order terms in this symbol over here, this big O. And it says everything out here is eta squared. So it's all higher order terms. And we're going to assume that we're going to assume that eta is small. So we're going to only look at etas that we don't, if we're squaring eta, squaring a small number, it doesn't matter. It's going to be really close to 0. Okay. So what is this? So what's that term I put a blue bar under?
It's the action for the real path.
Exactly. This is S bar, the real action. Okay, that's nice because now we can define our variation in our action. That's terrible. now we can define the variation in our action as S bar minus S. It's the first variation because we didn't include any higher order terms in eta. The second variation would only include the eta squareds. The third variation would include the eta cubes, blah, 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 blah. All right. So now the first variation is equal to this integral from T1 to T2. I'm going to move that out of the way for you all. So hold on. All right, let's try that again. Is equal to m dx bar dt d eta dt times eta v prime x blah 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 dt. So just what's left over there. Okay, we're almost done. And this last part requires some math that you might have forgotten. And so if you're lost, just follow along and you can check it out later. But we're almost done, and hopefully the reveal will be exciting. We know that no matter what value eta is, this integral must go away for our body to be in equilibrium, right? We know that the difference between the imaginary path and the real path has to be 0 if we're in equilibrium, or if we found the true path, right? Our imaginary thing minus the real thing has to go to 0. So, and we know that eta can be any arbitrarily chosen variable that we can think of. We just pick any value for eta we want, and we can just put it in there. So the only way that this integral can be 0 is that whatever multiplies eta has to be 0. Because eta can't be 0, it can be whatever we want. So the only way for this thing to be 0, which needs to be 0 in order for us to be in equilibrium, this needs to be 0. Whatever multiplies eta, oops, must be 0. And so we have this problem here. We know that eta can be arbitrary, but we don't know anything about this term. We don't know anything about the derivative of eta. And we have an integral of a derivative. We have a little trick we can use here where we can rewrite this integral by integrating by parts. This is important. You don't need to remember this now, but I promise you somewhere towards the end of the semester, this is going to come back. So if you don't remember how to do integration by parts, go look up how to do integration by parts, because it's basically we do two things: Taylor series and integration by parts. Remind yourself, it's the integral of how do I want to write this? We're going to do this as the integral of u dv is going to be equal to uv minus the integral of v du, right? Why am I doing this? I'm doing this because whatever multiplies eta has got to go away. We have eta here, great. We need to get this this thing into something that has eta in it instead of a derivative of eta. And we can do that pretty quickly by integrating by parts. And so I'll do that right now. So in terms of what we're writing, we would say the integral of did I do this in a dumb way? Let's see, I probably did. Yeah, okay. The integral of m dx bar dt times d eta dt over dt. So here's my u, and here's my v, or dv, should equal eta times m dx bar dt minus the integral of eta d by dt of m dx bar dt. All right, almost done. And so what do we want to say here? What we want to say is that oops, let's see here. This term, let's see, I should probably, oh, sorry, I should put the actual integration limits here. T1, T2. So this term we can deal with really quickly. What was the first thing I said when I drew up those pictures of the trajectories? What is eta at T1 and eta at T2 equal to? If you can't remember, go back up and look at the picture.
0.
Yeah, it's equal to 0. So this term goes away. So that's nice. So I'm left with my action. Let's go over here. I'm left with my first variation of my action is going to be equal to the integral from T1 to T2 of negative m. So we're saying m doesn't vary. Look over here. This term becomes m eta times the second derivative of x, oops, with respect to t. And so I have m second derivative, oh, I keep writing that. Second derivative of x bar with respect to t minus v prime of x bar, and I factored out eta, and that needs to be equal to t. If you remember what I said just a few seconds ago, right here, I'll highlight it in green. Whatever multiplies eta must be 0. Whatever multiplies eta must be 0. So that means this thing must be 0. And we can rewrite this. We say this is dx bar dt minus v prime of x bar equals 0. What's the derivative of potential energy with respect to in this case, time? Or what's the gradient of a potential?
The force
The force.
or negative force.
So this is a force. What's this? This is a force. What's this thing?
It's an acceleration.
Acceleration. So we just derived, after a bunch of math, not using anything of Newton's laws, we just derived F equals ma using the variation, calculus of variations. A completely different way at arriving at the same laws that Newton used when considering just how do you throw a ball. And we use the virtual displacements as a way to kind of do a mathematical trick, right? The mathematical trick was, I need to figure out what the potential and total and kinetic energies are, and I need to make sure they're at a minimum. And the only way I do that is I multiply them by this pretend term eta here. That can be any variable. And so if we say whatever multiplies that has to equal 0, then we arrive at the Newton's second law. Force is equal to mass times acceleration. Hopefully this gives you an idea of what these virtual displacements mean and how this works, because this is typically how a derivation like this would work, where we would basically make a pretend thing, calculate it out, integrate by parts, pull out all the pretend things, and then set whatever's left over equal to 0, and we arrive at the final equations. So hopefully this gives you a conceptual understanding of how it can be useful to use these concepts of virtual displacements and virtual virtual strains. So that was a lot, but the last part there was hopefully just for you to kind of be convinced that you maybe conceptually get what this thing means a little bit here. The main thing I really want you to take away is what we did right at the beginning, which is just these concepts of virtual displacements lead to a principle of minimal potential energy. Principle of least action is the same. It's just that we don't, in structural mechanics, we usually ignore dynamics as a first step. But now we're doing the same thing. We want to minimize whatever the energy is in the system. All right. We're going to end here. Please, please, please be in contact with me. The situation is evolving quickly. I understand that all of you have stressors outside of this class. As I said at the outset of this class, this to me I'm viewing as just bonus. Anything that's going to help you either be distracted from current day events or be something that you've learned that can be helpful in your jobs in the future. Don't think about stressing about grades for this class anymore. Think about, let's just learn. Let's just get something out of it. If you get 5% of what I'm talking about, that's better than 0. Let's just make this a place where you can come, spend like an hour, hour and a half, learn something new. I am not gonna try and pretend like things are normal here and I'm just gonna assess you in normal ways. Like that's kind of out the window. This is for you to just learn something. Come here with questions. If there's stuff you want to learn that I'm not talking about, send me an email. I can change, we can just do different stuff here. We can do, I can dig into stuff that you're interested in. I can try to find this to be as useful to you as possible. I appreciate your flexibility in this, but the thing I mainly ask of you is just be in communication with me. Let me know what you need. Let me know what would be helpful. I will try to do the same, especially if I hear anything else. But thanks for being flexible, joining me on here. I will send you these notes as soon as I can. I'll try to send you some form of a video or maybe audio. I'm not really sure what's gonna come of it, but I'll sort that out. But thanks for coming, everyone. I'll see you all on Thursday, and email me with any questions or concerns you have. All right.